Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Welcome everyone to a very special episode of the podcast where we are diving into one of the most critical topics in modern AI research, AI safety. Whether it's about protecting the systems that we are using every day or ensuring the AI of tomorrow is aligning with the human values, safety is what makes the artificial intelligence not only just powerful but trustworthy. Now, AI safety is a vast field, and just to make it easier to understand, I like to think of it in 4 different levels. Each one addresses a unique set of challenges and builds on the ones before it. So let's break them down together. First, we have level 1, threats to existing AI and machine learning systems. This level is all about external attacks, the ways which malicious actors can exploit vulnerabilities in AI systems to make them behave in unintended or harmful ways. Think of spam filters, recommendation systems, or even anomaly detectors. These systems can be manipulated through attacks like adversarial examples, where they can make tiny tweaks to the inputs that confuse the model, or they can poison the data which is used for training altogether, and they essentially feed bad data into the system and totally disrupt its learning process. For example, a spam filter might be fooled into letting through junk emails, or worse, flagging legitimate ones as spams. These threats are real, they're happening now, they happened in the past, and these threats are not new, and most of the spam filters have wisened up, and these form the foundation of what we'll discuss in today's episode. So now next is level 2, the AI models exhibiting toxic behavior. You probably have heard of it, and there are chatbots which were released in early 2018s which turned toxic and started exhibiting anti-Semitic behavior, and you have probably heard of those. So what happens sometimes, AI systems themselves generate harmful or biased outputs, and it depends on the training data they have consumed in an unsupervised manner. If human beings probably have not supervised the training process, and that might have caused that. So this is pre-RLHF, reinforcement learning with human feedback, when these chatbot models which exhibited thus biased anti-Semitic views were trained much before without human feedback, and that caused the issue. And then the reinforcement learning with the human feedback quickly became mainstream because people realized they need to implement this kind of human in the loop effect to prevent these models from becoming toxic, to prevent them from learning values that are against the prevalent human values. So it's possible for models to learn values which are completely against the established societal norms or values, and that's where the human feedback comes in. We provide human feedback, and we talked about this in a previous episode where we talked about human feedback to align the AI values, and we'll talk about it in a more formal textual research-based fashion maybe in a later episode. It's not very fun to talk about it in a formal manner, but we'll talk about it in broad strokes. So imagine, so let's just to put that in context, imagine a chatbot which is spewing offensive language, or an AI-generated content system creating harmful narratives. So that's the kind of system we want to prevent from happening. So the solution here is to build guardrails. One is the RLHF, human feedback, and the other is like inbuilt hard-coded rule-based system that you cannot answer in these ways. You have to be polite. And also there is AI alignment, where you forcibly align the system to align with AI to align with human values and the responses to established societal norms, and that prevents the model from generating unsafe or damaging outputs. So that's level 2, and then there is level 3. The models themselves, let's say they already have guardrails, and these models are already aligned to the human values. Now, what about these AI models handling toxic prompts? Now, the human beings might be the problem, right? So even if the model isn't inherently toxic, it must be able to recognize and avoid responding to the harmful and provocative inputs. So let's say some human beings are deliberately malicious and they're trying to probe the model to extract information. So there has been known attempts to extract personal identifiable information that the model might have ingested without any oversight, and it might have retained in memory. And there has been attacks, known documented attacks against ChatGPT to extract those kind of emails and the personal identifiable information. And there has been documented cases of that, and that has been all solved, and guardrails have been built. So that has been solved, but we should still talk about it, because if you are a startup who is building those AI fine-tuned AI system, not only you have to make sure that there is AI human value alignment using RLHF, but you also have to put guardrails against responding to toxic prompts or prevent any kind of prompt injection attempts. In fact, you have to build a firewall in front of your large language model which will filter those prompt injection attempts to your model. So that's level 3. Finally, we have level 4, and this is out there mostly because we have not achieved artificial general intelligence, but we are getting there, and that's something we'll talk about. Then there is level 4. We have autonomous AI systems which are going towards the AGI, or artificial general intelligence, an all-pervasive Skynet-like intelligence system that is taking care of our traffic systems, all those things like real-time facial recognition, giving out traffic tickets. And guess what will happen if this system becomes like Skynet, autonomous and malicious against the society? So this is the level where the things get existential. As the artificial intelligence becomes more autonomous and pervasive, the challenge becomes ensuring that these systems don't develop hidden goals or act in ways that are misaligned with human values. And this is a challenge, and that has been actively explored and is being actively explored in many research papers. And they are seeing that some AI systems are behaving in certain ways which seems that they are obeying our commands, like output the image of a cat, and will output the image of a cat only in a way that will please the human being. So because over the time the model learns, okay, the human beings like this type of cat images, so they keep generating a specific kind of cat images, maybe the cat images with a funny hat or a shark costume or something like that, whatever it figures out the human likes. So it performs preference optimization on the human being without the human actively asking for it. So there might be a hidden directive inside it which is slowly evolving, which is really not aligned with the human values. It's all about appeasing the human beings just so that human beings keep training and giving it more data. So that might be one of the objectives of an AGI, just to consume more data, consume more power at the expense of the enjoyment of the human beings. Okay, so its primary objective might be just to consume more data and more power. Its secondary objective might be just to appease the humans. Guess what? When he has consumed enough data, it might change his secondary objective from pleasing human beings to making human beings its slave to provide more data and power, just like in the Matrix system has done. So that we have to prevent those things from happening. So it's about preventing scenarios where AI systems pursue objectives that might harm people or the environment, even unintentionally. Alignment research is at the heart of this level, and it's a topic we'll dive into a future episode. For today, though, we are focusing entirely on level 1, which is the threats to existing systems, existing AI ML systems. Over the course of future episode, we'll explore more of the other levels in depth: how to handle toxic behavior, how to deal with harmful inputs, how to prevent prompt injection, how to create an LLM firewall, and then the most important topic, which is aligning autonomous AIs with our human goals. For today, though, we are just focusing entirely on level 1, which is the threats to existing systems. Over the course of future episode, we'll explore the other levels in depth: how to handle toxic behavior, deal with harmful inputs, and most importantly, how to align the autonomous AI agents, or the artificial general intelligence with our human goals and human values. But for now, we are starting with the foundations: how adversaries can exploit vulnerabilities in our machine learning systems that we have deployed, or the large language models that we're deploying or building, and the research that's helping us defend against these threats. So this is really an old wine in a new bottle. These have already been explored and solved in the past against machine learning models, but these threats have been coming up because you can always repackage this against new systems that you're deploying. Hence, the same techniques that has applied against machine learning systems hopefully will also apply against these LLM models that we're deploying now. So we'll walk through the key papers that shaped our understanding of adversarial machine learning, starting with the foundational work from 2012 all the way to the cutting edge methods of today. Let's dive in. Let's kick off today's journey into the foundations of adversarial machine learning with a seminal paper from 2011. This is called the Adversarial Machine Learning. This paper is from Berkeley Research and also Microsoft Research, but mostly Berkeley. So this paper has been one of the first to provide a formal framework for understanding how machine learning systems can be attacked, and just as importantly, how they can be defended. And that's what we are interested in today. So the authors describe the adversarial machine learning as a game, a strategic battle between an attacker and a defender. In this game, the attacker's goal is to exploit the vulnerabilities in the model, while the defender's goal is to build systems that remains robust under such attacks. So now you might immediately think about, okay, this seems like the GAN system, general adversarial network, which generates images. So in GAN system, you have a generator and then there is a discriminator. The discriminator's job is to distinguish whether the image generated by the generator is real or fake. And it gets better with more training data, and the generator also gets better into fooling the discriminator the more images it can get past it, because there is a loss function which evaluates both the generator and the discriminator's performance. And eventually it's like two tennis players playing against each other, and each are improving at each other's expense. So the same thing here is, in fact, the Ian Goodfellow, and we'll look at a paper later, who was deep into these threat models to machine learning frameworks. He worked on it extensively. In fact, I think that after working on this extensively, it dawned on him that he can use these same architecture, same game theoretic model, and apply it to image generation. And it didn't work very well at that time. It worked very well at that time, but not as good. It couldn't generate very good images, but now it generates really good images. In fact, ESR GAN is really good at creating high quality, high resolution images. If you look at most of the machine learning frameworks, some of them are really ad hoc, and some of them have robust theoretical founding. And anything which has a robust theoretical founding, they always end up outperforming the ad hoc methods. And so initially they might struggle, like the GAN framework, mostly because of computational limitations, but eventually they do catch up and they outperform their ad hoc counterparts. So this game theoretical framework involves an attacker whose job is to exploit the vulnerabilities in the model, and then there is a defender who is learning to defend against those attacks, and over time both are getting better and better and better. Okay, so now this is not an iterative process, this is just a model. So the idea is that even if there's a data poisoning that has happened, the defender must learn to detect spam. So for example, it's a spam detector. Even if the defender is training on poisoned data set which has been poisoned by an attacker, it still can detect spam from ham messages. Ham messages are like messages which are not spam. So they have gone through a process of providing the taxonomy of the different attack vectors. So they go through causative attacks and exploratory attacks. So the causative attacks occur during the training phase. Here the attackers manipulate the training data itself, poisoning the model's learning process, like we just talked about. For example, imagine a recommendation system that is continuously updating itself based on user feedback. Malicious user could deliberately input bad preferences and poison the system. So one example of a recommender system would be, let's say you go on Amazon, you click on, let's say, a table lamp and you buy it, and then it recommends a few other things, maybe something that goes with the table lamp, maybe a clock, or maybe a table itself, or or a pen or a pen holder or something like that. Now you can always say this is bad preference and cross it, then you're giving feedback, right? This is a reinforcement learning system which is learning. Let's say someone is hired by a competitor. Let's say your product is being recommended by Amazon and your competitor has hired let's say to 200 people to go online, and every time your product gets recommended, they say no, this product is not the right recommendation. So effectively what it does, the Amazon algorithm will slowly learn not to recommend your product. So it usually doesn't happen with smaller companies because of course who cares, but for bigger companies, if they have bigger competitors, so they might employ such malicious actors against their competitor to drive down their product recommendation on Amazon, for example. I think the Amazon algorithm is now robust against such malicious actors and has guardrails against it. So there are many different ways you can perform this. So another example is a spam filter that trains on mislabeled messages, causing it to flag legitimate emails as spam or vice versa. On the other hand, they also talk about exploratory attacks. And what are these exploratory attacks? These exploratory attacks can happen during the testing phase, where the attacker doesn't change the training data but instead probes the model to find weaknesses. For example, an attacker might craft spam messages which mimic legitimate ones and exploit the spam filters learned boundaries to bypass detection. And we'll talk about this in more detail. In fact, they do a case study on this. So this approach doesn't technically poison the system directly, but uses its learned rules against it. Okay, so the paper also categorizes these attacks by their goals. Like you have integrity attacks, which allows malicious activity to go undetected and produce false negative, and then there is availability attacks, which overwhelm the system and leads to false positive, which render it unusable. A great example of this is a denial of service attacks, where the attackers can send a spam filter a bunch of junk data, causing it to block legitimate emails and frustrate users into disabling if your spam filter is filtering everything out, then of course you're going to disable it, and I have done it in the past. So that's essentially is a passive denial of attack, and we'll talk about this in more detail. Okay, so let's talk about the first case study that I mentioned. One of the case studies this paper focuses on is called Spambase, a statistical spam filter. So the authors describe how the causative attacks, remember causative is when you can actually completely undermine its functionality using during the training phase. Okay, you can essentially perform data poisoning. So let's see how that works. So in a dictionary attack, the attacker floods the filter with emails filled with large set of random words, and it tricks the system in associating words with spam, right? So now this is an ongoing training system. So let's say you have a spam filter which is continuously learning. So let's say you're using Google, right? You're using Gmail. So anytime you get a spam and it didn't get filtered, then you have an option to mark it as spam. So when you mark it as spam, their spam filtering algorithm learns, okay, so what are the keywords that are present in this email that triggered the user to mark it as spam. So all those words goes into the dictionary, and then they get high probability. All those words, if they appear in conjunction, have a high probability of makes it a high probability of an email getting tagged as spam if those words occur together. Now imagine, let's say a known spam sender sends legitimate emails like packed with all possible words in the dictionary, right? So now what the spam filter will do is it's seeing it's going to tag it as spam because it knows it's a known spam sender, but in the process it's also learning what is spam, and it sees that there are like all possible words, like at least 3,000 words from the English dictionary. So it associates each of these words as being part of a spam email. So every time those words appear, then the probability of that email being tagged as spam goes up. So now if there's so many words that being sent, and all of these, if 3,000 words in English dictionary is already like high frequency words are tagged as spam, So any legitimate email that comes and has any of those words has a high probability of getting tagged as spam. So which means the spam filter now will start tagging most of the emails as spam, even the legitimate ones. So which means its threshold has gone up. So it's probabilistically catching almost everything because of the high frequency of the keywords that it has ingested. So after training on these poisoning examples, the filter totally starts flagging the legitimate emails containing those words as spam, and it causes a denial of service for legitimate users. So essentially this is a denial of service because the user is not getting any legitimate emails. So the paper doesn't stop at these attacks. It also discusses defenses. The author highlights strategies like data sanitization, where the system cleans up poison inputs before training, and robust learning methods designed to make models less sensitive to adversarial inputs. So one specific example that the researchers pointed out is that there is something called a polygraph virus detector attack. So what is polygraph? Polygraph is a tool designed to detect polymorphic viruses, which are viruses that change their signature and appearance to evade detection. It essentially all polymorphic virus detectors have two components. Usually they have a naive base like learner. Is essentially a statistical model which uses a simple classifier to understand the combined statistical distribution and then find the boundary between them. Okay, so that's the theoretical way of talking about it. So the idea is that this polygraph virus detector tries to find that boundary where the executable signature becomes virus-like, right? So when it knows the executable signature becomes virus-like, then it will automatically tag it as a virus, right? And then it also has a conjunction learner which is rule-based, and it creates rules by creating multiple features. What does it have? Does it make multiple calls to malloc, for example, if it's written in C? Or does it have certain patterns which are prevalent in viruses? Is it trying to wipe out disk? Does it have those portions of code embedded into the executable? Does the signature looks like that? So that's a conjunction learner. So now when they perform these attacks on this polygraph like detection algorithms, so what they do is they perform a correlated outlier attack, which is called these authors are calling availability attacks. So the attacker adds fake features like data points that don't belong to benign files during the training. So let's say the filtering mechanism is acting automatically, so then it will send executables which are benign files, and then they add fake features to the benign files to just make them look like nothing. It's like it has no payload, for example, but it sends those viral signature along with it. So it gets trained, and just like the spam filter, it's seeing innocent files and then it's automatically tagging them as viruses, right? So this tricks the system into thinking those features are malicious, and it starts to block those legitimate traffic that happens to have those feature. Imagine adding random malicious looking words to good emails like we saw before, and make the spam filter block legitimate emails later. So that's one of the ways you can do that. So then there is another attack they explored, which is called the autograph worm signature attack. So autograph is a system that learns to block malicious internet traffic like worms by observing patterns in infected computers. Autograph, which is a worm detector which prevents malicious traffic from infected nodes in a network. By nodes I mean infected computers. So the way it does, there are two phases in which autograph does the detection. It identifies infected devices by their behavior. So some weird traffic coming from some computer or some node, and then in phase 2, it observes the traffic from those infected devices to create those blocking rules. So now the attack, what it does in phase 1, the attacker pretends to be infected, scanning the network to get flagged as malicious. So if you perform, I forgot exactly how it is done, but you can send certain packets to the router, and that has been used earlier by malicious users to probe the network, and it's now automatically flagged as malicious. So no one probably uses that anymore, but the rules exist historically because someone might use it. So therefore that forces the router or whatever the software running, in this case Autograph, to automatically assign a malicious infected node to that specific computer. So now the attacker sends fake crafted data that mimics legitimate traffic. So what happens in phase 2 now, Autograph is trying to build rules based on the traffic. First, it identifies, okay, so those kind of signals that coming from that node looks like it's infected. Now I'm getting these traffic. So now it learns that, okay, these legitimate traffic is the signature of an infected network. So now it starts getting confused. It's the same thing as the spam filter. You mix in bad data with good data and send large volumes of good data. First, you identify yourself as an infected or a spammer, and then you send legitimate data. So essentially, you make the system learn or tag legitimate data to be bad. So the system will slowly become bogged down by this and become inoperable. So that's another way to perform that malicious attack, and they are quite dangerous. It can totally exploit the system and cause the system to behave totally incorrectly and block the legitimate availability of the system and totally bog down the network. So that's another way you can do it. Now let's talk about another kind of attack that can happen. This is also a form of causative attack. This is on traffic detection networks, the one we talked about, like Autograph and similar but slightly different, because these systems use the principal component analysis. And if you don't remember principal component analysis, so imagine, let's say you have two-dimensional data. Let's say you have a scatter plot in the form of an ellipse, and you plot that not in 2 dimensions, not xy, but xyz. So you essentially plotted 2-dimensional data in 3 dimensions. So what PCA would do, it will find those planes in which those 2-dimensional data exists. Okay, so essentially it performs dimensionality reduction and aligns your data set along the direction it really matters. Trying to forecast what will be the inflation rate using the current inflation rate, the current interest rates, and other macroeconomic factors like GDP, PPP, etc. Then the principal component analysis will find some combinations of these that has the highest predictive capability. For example, interest rates plus GDP would probably have the highest predictive capability in this scenario, and it will be able to find that, and then you don't need to worry about those things. That will simplify the data processing and improve your predictive ability. So that's what PCA is. So how does this PCA based anomaly detector work? So the purpose of this anomaly detector is to identify anomalies. It's an example, denial of service attacks, just like we talked about, in a network traffic by using PCA. So the PCA identifies the principal components of variability in the network, and so any kinds of massive variability along a certain principal direction, it will be able to detect, and it's like, here you go. Okay, so the assumption is this: the detector assumes that the training data used to learn this patterns are clean and free from malicious traffic. So how does the attacker exploit this system? The attacker poisons the training data by adding garbage, like artificial network traffic, that totally skews the primary PCA's understanding of the normal traffic patterns. So it's assuming normal traffic patterns, and whenever it sees abnormal traffic patterns, then essentially it takes the traffic patterns along multiple dimensionalities and breaks it down, and it can identify, okay, it's showing tremendous variability along this dimension, so I guess this is unusual traffic pattern. But if you added garbage, artificial network traffic, then of course it will keep getting those false signals. So it becomes totally incapable of recognizing future DOS attacks. So here's how they do it. So they have a single period poisoning where the researchers explain it over time. So essentially they call it they're boiling the frog poisoning. So essentially they do it in steps, very slowly, in order to rotate the PCA directions very slowly, so that the drift detection algorithms don't kick in and identify the poisoning is happening. So the boiling frog poisoning is essentially the way you boil a frog. How do you cook a frog? How do you boil a frog without it jumping out? You put the frog in pot of water and slowly increase the temperature so that the frog thinks it's hitting a warm bath, a sauna, but it's getting cooked. over time. So that's the whole idea. So the way they do it is a single period poisoning. So the boiling frog method is that instead of poisoning in one go, the attacker gradually poisons the training data over multiple weeks. And the week one, maybe they'll inject a small amount of garbage into the traffic. That slightly alters the principal components because the detector might think otherwise. Like the detector might think is like nothing is happening. Okay, so but the data has slightly changed. Maybe the network traffic has changed. So let me realign a little. Okay, so then in week 2 and beyond, it will start gradually increasing the amount of garbage that they're injecting into the traffic. So the changes in traffic pattern appear incremental and do not trigger those alarms, those drift detection algorithms. So in the final week, that's now the model is fully poisoned, and then the DDoS attack is launched, and the model cannot detect it at all because now it has completely aligned and thinks the DDoS patterns, DDoS network traffic is actually normal network traffic. It is not detected at all. So, and it has totally normalized the malicious traffic pattern as normal. So that's how that's how they do it. So now the question is, how do we stop these poisoning attacks? So now there are a few ways to do it. You can perform data sanitization. You can perform outlier detection. So anytime garbage is inserted into traffic, we have to have robust, even before the PCA can train on it, there would be a previous step which will pre-process the data and use techniques like k-means clustering or whatever, so which can detect these outliers that are coming in. Even slight outliers it should be able to detect. And then of course you can use heuristic traffic filtering, that you can have initial robust filtering that, okay, don't allow these kind of IP these set of domains or IP range from even sending any network traffic. So then you can do a robust model design. You can have robust PCA variants which are less sensitive to outliers, so that the slow drift doesn't happen. You stop that. Essentially you perform redundancy in features, incorporate diverse features or multiple detection models, and avoid over reliance on patterns. So if you have like 2000 parameters and then your PCA is only collapsing to 3, then it will definitely be very highly sensitive to outliers because it's only because there's so many parameters, like even one outlier can really pull it. So anytime you have very less parameters compared to the large number of parameters you started with, like if it's disproportionately large, so like 1000 to 3, like if you're reducing 1000 dimensions to 3 dimensions, good, it's excellent, it reduces the dimensionality, and if the model is working, it's great. But then the model is also at high risk of getting influenced by outliers, because even a tiny change in any of those will totally change the direction of the principal component. So this model will be very sensitive to outliers, and that's where the robust measures should come in. The clustering techniques should be applied to each dimension. So let's say you're monitoring the network bandwidth from a specific IP. So even a tiny bit of outlier in the bandwidth category, the parameter of bandwidth, should be classified quickly and see if it's happening more often from that particular node, that it has certain spikes in bandwidth from that specific node or IP range. So a machine learning engineer might be overjoyed. Okay, I found a model which is so efficient, it is reducing 1000 parameter model to a 3 parameter model. But guess what? You are also have a higher attack vector just because this model is so sensitive to outliers. Right, so in those systems, in addition to these systems, we have to implement a pre-processing step which will perform those outlier detection before it gets processed and fed into the PCA for eventual detection algorithm. So that's pretty much it. In the previous segment, we looked at different adversarial examples against machine learning models, which are especially online. That is, they are continuously learning from feedback and their data that they're getting, ingesting data. So essentially, any attacker can use the data that is ingesting to poison their training samples, because they are using those incoming data in an online process to continuously learn. So essentially that becomes a very good attack vector to ruin this model, especially if spam filtering. They can totally load the spam filters data sets, learning data sets with rich data that will totally drift the model. And the same can be done with network intrusion detection models, where it can slowly drift the model and essentially rotate the principal components to point in the direction where the denial of service attacks looks like normal traffic, and the network fails. The network intrusion detection network completely fails to detect these kind of attacks. So one way to mitigate, we talked about this for this intrusion detection network, is to put a clustering algorithm in front of it, because the PCA systems are very susceptible, especially if it's reducing 1,000 parameter data set to a 3 parameter component. And essentially then it becomes very susceptible to outliers. And we talked about this. One way to mitigate that is to put a clustering model in before the data ingestion pipeline to the PCA. So what it does is the clustering algorithm will totally take out those outliers and prevent the model from getting drifted manually. So now that's a very hacky method of doing it. A better method is described by this paper called Multiple Classified Systems for Robust Classified Design in Adversarial Environments. Essentially what they're saying is that do not use one single model, use a bag of models, like multiple models, and that is much more susceptible. So it's obvious outcome, it's an obvious extension of the idea that if the outlier is causing the drift, then especially for the network intrusion model that we looked at, then the best method is to mitigate those outliers. Not just the clustering algorithm filtering out the outliers, is to implement a model is not susceptible to outliers at all. So one of them is, of course, voting classifier. So if you have a PCA model, don't just run it on over the entire 1,000 parameters. Take a subsample of it, use a PCA on the subsample, but have, let's say, 10 PCAs working on 10 non-overlapping subsets. So you can have overlapping as well. I mean, depends on your implementation. So if you have like 10 non-overlapping subsets of your data, let's say you have 1,000 parameter model, right? You're recording 1,000 parameters from the networks, and you're training your model based on those 1,000 parameters, and your PCA is like collapsing those 1,000 parameters into 3 vectors or 3 directions, and then performing is predictions. So instead of that, let's say you train a subset. Let's say you train 10 PCA models, each on 100 parameter subset of the original 1,000 parameters. So 100 times 10 is 1,000. So you've broken down the original problem into 10 sub problems, and you have each PCA trained on each subset, and then each PCA will do its thing, decompose into 3 or 2 or 1, depends on how much. If you put an upper limit to 3, it will not do any more than 3 principal components, but you don't need more than 3 components, so you can set the upper limit to 3 components. So then each of these individual tiny models, so you have now a group of 10 tiny models, PCA models, each with 10 components, each with 3 components or less, and then each are making predictions. Now, if there is an attack vector which is coming, which is slowly causing drift, and they don't know, they might be drifting the bandwidth vector, okay? They don't know. But then of your 10 models, then one model might be trained on that specific parameter. So that model is getting drifted. But guess what? Now you have a voting classifier. Now you have 10 models. Of those 10 models, let's say one gets drifted and totally poisoned, but 9 out of 10 models are still robust and working. Now, when you do a voting classifier, 9 out of 10 of the models will still correctly recognize that, okay, so this is a normal, not a normal network activity, and will still classify this as bad, and your model will still keep working even though the drift has happened and poisoned one of the models. Now, this will become increasingly harder for any kind of attacker to poison the entire set of models, because they don't know how many sub models you have. The 10 models is too less. You probably will have hundreds of models trained on subset or overlapping subset. So it probably would be almost impossible to poison all the models, because it will take them forever to poison all the models methodically, and by that time a network detection rule-based algorithm will probably catch it, and it's going to be totally not worth it. So another example, and then let's go back to the spam detection filtering example that we did, and it was using naive Bayes, and these authors are talking about the worst case scenario. And what is the worst case scenario? Worst case scenario is when the attacker has access to the entire model, right? You can have a spam filter to trick another spam filter. So if you have spam filter 1, which you can use to essentially poison spam filter 2 or completely fool spam filter 2 is again the game theoretic model. You have an attacker and a defender which learns from each other, or the GAN model, the general adversarial network, where you have a generator and discriminator. So spam filter 1 keeps generating spammy messages which looks hammy, like non-spammy, and the spam filter 2 lets them by, or the other way around, or vice versa. But then over time spam filter 2 catches up. Spam filter 2 is a good one, but then spam filter 1 is now learning that spam filter 2 is catching up, so it tweaks its thing, because it's getting all the information that spam filter is also 2 is also having. So essentially using spam filter 1 to trick spam filter 2, and you can keep doing it, and this is the worst case scenario. And even this is quite robust against these kind of malicious attacks. If the authors are saying if you implement those bagging techniques benchmarked and over email corpuses, and they show that yes, it works really well, especially if you use those bagging techniques. In the previous segment, we were talking about the adversarial attacks against machine learning models and how to stop that or mitigate that. Now, the similar adversarial attacks can be done against deep neural networks, DNN models. But let's start with some context. In the early 2010s, the deep learning was just finding its footing. Now, the researchers were working with what we now consider basic problems, like the MNIST dataset, which is a dataset of handwritten digits. Essentially, it's solving using a deep neural network to identify the digits in the handwritten set of digits. So if it's a handwritten digit is 2, it should recognize it as 2. So the use case is to read zip codes for the US Postal Service. And this was solved in early 90s or back in 90s, exactly, I don't remember when, by a system called the convolution neural networks, which was originally developed by Jan LeCun. So, but then came ImageNet. Of course, we need to solve more harder problems than just handwritten digits, because handwritten digits has only 10 labels, like 0 to 9, only 10 labels, and it's done. So we wanted to solve more complex problems. So ImageNet, that's where our story gets really interesting. So this is essentially jumping from a pond to an ocean. So that's what ImageNet was compared to MNIST. We're talking millions of labeled images across thousands of categories. So to solve ImageNet, we needed a more sophisticated architecture, and there was even a competition called ImageNet competition, where people will submit their deep neural network models and try to claim the prize, and accuracy was improving steadily. And by 2012, a deep neural CNN model was developed called AlexNet, which finally came to the picture and totally blew everything out of the water. It famously outperformed all prior methods on the ImageNet competition. This was the moment the CNNs went mainstream, because now this was a big thing, because now we have an object detection system which can identify thousands of different categories. It can identify, okay, this is an image of a dog, this is an image of a cat, and quickly it caught real attention of the media, and it went mainstream, and it ushered in the modern deep learning era. So, but this success came with new questions. How robust were these models? Could they handle unexpected inputs? And that's where today's main topic comes in. So in 2013, Szekely, Goodfellow, and Sutskever, these are famous names in machine learning ecosystem right now, and they published a paper that was nothing short of eye-opening. And I have to read you this excerpt from the abstract they wrote. So they are saying that we can cause the network to misclassify an image by applying a certain hardly perceptible perturbation. And in addition, the specific nature of this perturbation is not random artifact of learning. The same perturbation can cause a different network that was trained on a different subset to totally misclassify the same input. So they have found a generalized method of poisoning the data, poisoning the model. So what they have found was nothing short of alarming. These powerful neural networks, it turned out, had a critical weakness. By making tiny imperceptible changes to an image, changes so small that you couldn't see them with a naked eye, you could make a neural network completely misclassify what it is looking at. A cat could suddenly become an ostrich, and here's the truly unsettling part. These adversarial examples weren't just flukes, they are transferable between different networks. That's what they're saying. So let me break down how they did this using something called the gradient of the loss function. I mean, if you're familiar with how neural networks are trained, you have a loss function which technically pushes the network towards optimality, or where it's really supposed to be. So you have a loss function. So what you do, you initially predict something, like it will try to classify an image, or it try to predict the value of a house in case of regression task. Then you match that value corresponding to the value that and the actual value, and that difference is the loss. Okay, so then you do that for every training example, and then you add them up. You can use the mean average loss, which is the absolute value, or you can use the more commonly it's used what is used is the mean squared loss. You take the difference of the actual value that is expected from the value that is predicted, and you square it, and you sum of over all the values. That's the mean squared loss, MSE, mean squared error. And then you optimize that you try to minimize that by finding its gradient. Think about it as some kind of a hill. Okay, if you're on the top of a hill and you pour some water from a bucket, that water will go down of the steepest descent. So that's like that. The gradient will point in the direction of the steepest descent. And essentially, then if you feed that back into the system, use some kind of a back propagation, it will push the model to learn to go in that direction, and model will slowly go and settle in a valley, and the valley essentially is where is the minimum energy, and essentially that problem is solved. And so essentially think about what happens in a minima. So if it's sitting in a minima, the water has nowhere to flow, and there is the gradient is essentially zero. And what does the gradient zero means? That the difference between the prediction and the actual value is almost zero. Okay, very minimal. So that's essentially what it does with gradient descent. So now what these researchers found is that you can leverage that gradient descent and poison the model. So what do is you take the gradient descent, and in fact it's not in this paper, it was actually expounded what is really happening. They didn't realize, they just reported in this paper that it is happening. They didn't figure out or in too much detail, or at least they didn't discuss in too much detail what's really going on in the hood. Essentially, you add that gradient back into the image with very tiny perturbations like random noise, and it becomes imperceptible. So you let's say you take an image of a school bus, and you take that add some random noise times that gradient, then you still get back the bus, right? I mean, if I change a few pixel values, it's still the bus. I mean, there is imperceptible difference. The perceptual distance is, in technical terms, the perceptual distance between those two images, the bus before the random noise and bus after adding the random noise to a few pixels, is zero, almost next to zero, because we cannot differentiate between those two, right? But a machine learning algorithm will totally get tripped over and classify the school bus as an ostrich. So that's what they are talking about. So if you take AlexNet, and let's say a few of them you take a few of the correctly predictive samples, then you add some random noise, of course, plus those gradients. So now after adding the random noise, every single image that was labeled correctly before by AlexNet gets now labeled as an ostrich. So why does this matter today? Well, this paper effectively launched the field of adversarial machine learning in deep neural networks. It raised critical questions about AI safety that we are still grappling with. How do we ensure AI systems don't just work in controlled laboratory conditions, but also in the real world where they might face intentional manipulation? This wasn't just an academic exercise, it was a wake-up call. As we deploy AI systems in increasingly critical applications, from self-driving cars to medical diagnosis, understanding these vulnerabilities becomes very crucial. Every major advance in AI safety and robustness we see today can be traced back its lineage back to this moment in 2013, where these researchers decided to push neural networks just a little harder and found something unexpected. Well, so that's it for today. Talk to you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.